ICHEP is the big international conference on high energy physics, and this year it was supposed to take place in Prague, but given the situation with the coronavirus, the committee has decided to have it as a full online conference. So it was the first edition of an online-only conference at that scale, at this large scale. They had something like 2,700 registered participants, so it's really a big conference. So at this conference, the ATLAS collaboration did report many new results based on the complete data set which was collected in the second experimental phase at the LHC. We have many new results on many areas of physics, starting from the Higgs boson, test of the standard model, going to use the LHC for the first time as a photon collider, and as well on searches for new particles, searches for new physics. ATLAS presented new insights on the Higgs boson physics. One of them is the constraint on decays of the Higgs boson into invisible particles. We addressed another rare process, which was a decay of the Higgs boson to a Z boson and a photon. And then, as well, very important, we presented final results based on the run 2 on the possible decay of the Higgs boson into fermions of the second generation. This, I think, is a very important result because so far we have seen the Higgs boson decays into bosons. These were the Discovery Channel of 2012, which is the W, the Z, and then also via loops into photons. And then over time, we got, for example, in 2018, clear evidence and observation of the Higgs boson decaying into B quarks and also coupling to top quarks. And now for the first time we get sensitivity to the second generation. We cannot claim evidence yet for this. However, we have a strong access at the level of 2 sigma to see an access at the right mass of the Higgs boson. On the Higgs, the large data set allowed us also to study the properties of the Higgs particle, because an important question is it really the standard model Higgs, or do the properties deviate in some way from the predictions of the standard theory? And here we have increased the precision. For example, the one measure is to look for the couplings, the strengths of the interaction of the Higgs with the standard particles. And here what is usually done is to introduce a scale factor which allows for deviations of this coupling from the standard model value. And these scale factors are constrained now to be standard model-like with a precision at the level of 5 to 6% for the W and Z bosons, and at the level of 14 to 15% for the fermions of the third generation, which is, I think, a big step forward compared to the precision which we achieved in run 1. One study we did is to look for invisible decays of the Higgs boson. Now you may ask, how do you see an invisible decay of the Higgs boson, or in particles that do not leave any traces in your detector? So there we have to use an analysis strategy where the Higgs boson is produced in association with another particle. So for example, there's one very nice study done in ATLAS and presented where you have the Higgs boson produced in association with a jet, or with 2 jets. There's one Higgs boson production process which is called the vector boson fusion, where you have 2 accompanying jets going in the forward direction of your experiment. And then what you see is missing energy. And this missing energy is a sign that something escaped detection. And then you look if your events where you have such a signature can be described by standard model processes. And this is exactly the case. So we see no excess beyond the expectation from production of standard model processes. And this is then allows us to constrain and set limits on the contributions of Higgs decays to invisible particles. We look more generically for missing energy events. For example, if we see only one jet in the event, this is what we call a monojet signature. And this monojet signature is very striking. You see, for example, we have a nice event recorded where you have an 800 GeV jet going in one direction of the experiment and nothing on the other side. You obviously know there's missing energy. Now, this could be dark matter going away on the other side, but of course it could also be background, which you expect in the standard model. For example, a Z boson produced in association with a jet and the Z boson decays to neutrinos would give you a background event. And now we have estimated the background events and came to the conclusion that our data can be described by the standard background contributions. So there's no room for a large contribution of dark matter. And this allows us to put up constraints both on the Higgs boson decay and also on the direct production of dark matter. Another major highlight which Atlas presented at ICHEP was first results and observations of interesting processes based on light-by-light scattering at the LHC. This is a process which should not happen in classical electrodynamics. Light should not interact with itself. However, in quantum electrodynamics, you have a possibility. It's one of the early predictions of quantum electrodynamics that you can have interactions light by light. And this was seen for the first time at the LHC at the high energy in 2019 and published by Atlas. Now we can use the light-by-light scattering to produce massive electroweak gauge bosons, namely a pair of W plus and W minus. And this process was observed now with a high significance above the discovery threshold by Atlas. So you can ask, why is this process so interesting? It's first of all interesting because you have here in the Hadron Collider environment, where you have protons, quarks and gluons, you basically can isolate an electroweak process. You have a radiation of the photons from the protons, and these photons then interact. And they interact directly in the self-coupling of the gauge bosons. And this in a very clean process without what we call an underlying event. Because you do not break up the proton, you do not perturb any of the quarks inside the protons remain intact. And then you see the electromagnetic process. It reminds you a little bit to the cleanliness of the interaction processes which you see normally or are used to see in E plus, E minus colliders. And since the proton remains intact here, there is another experimental technique you can exploit. You can basically look whether you can detect these protons which have radiated the photons. And for this, the Atlas experiment has designed a special spectrometer. We call it the AFP, the Atlas Forward Proton Spectrometer. In a different process, not with W pairs in the final state, but with lepton pairs in the final state, we have seen the first physics result, which is based on detecting as well the protons in these forward spectrometers. So the light-by-light photon collider aspect of the LHC has been used now in two observations by Atlas, the observation of the W pairs and the observation of lepton pairs with the accompanying detection of the forward protons. And I think these are very nice results and shown for the first time. Atlas has for the first time looked into lepton flavor universality. In the standard model, you basically predict that the interaction strengths between the various types of the leptons is identical. It doesn't depend on the lepton type, it doesn't depend on the mass. So the electron strengths, the muon strength, the tau strength should be identical. And this is called lepton flavor universality. There was a result published about 20 years ago by LEP, the combined result, where there was a 2.7 sigma tension on the interaction strengths that the W decays differently to tau compared to muons. And we have checked now on this result. We have used here the large number of top pairs which are produced at the LHC. LHC is really a top factory. And this large number gives us access as well to Ws, because the top nearly to 100% decays into a W and a B quark. And then we can use these Ws to look at their decays into muons and taus. And this is a new analysis technique which was designed now by Atlas, and we have got a very nice measurement, namely a result that the ratio between the WTKs to muon and tau is respecting unitarity. We find a result which is within 1.3%, very close to unity. And the amazing thing is that the precision reached there at the LHC is now a factor of 2 better than what was reached at lab. So this was a very nice first batch of results that we released now at this ICHAP conference, but we are not done yet with the analysis of our large run-2 dataset. We will continue to look in searches in more complex areas of parameter space. And then there is the area of precision measurements I just mentioned, and there we are definitely not done. These analyses are complex, need a careful assessment of systematic uncertainties, and the work there will continue. And I'm sure Atlas will present another nice suite of results at the next conferences.